tuwandikire ku namba z'essimu ez'owammanga.
Weewaawo mbaniriza nnyo nateera ku programu ya leero. Programu somera mu Muddiirolyo ssaawa ziri 9 bwe budde Ssaabasajja bwe yasiima n'awaayo okulaba nti tubeerako n'enteekateeka eno eyongera okulungamya ebyenjigiriza eri abayizi abaakosebwa olwa ssennyiga ono omukambwe. Weewaawo sibalwiseeyo. I want to welcome you all to today's show. Since it's a Wednesday, we are having a discussion in Physics Paper 1. I'm still tackling the part of heat, introducing the Form 5s to the concepts of thermometry, and then later on I'll also be running through calorimetry. Like I promised at the beginning of the section that I'll be looking at the different types of thermometers, the thermometric properties that they use, and then also doing some calculations, which was what I did, I think, on our previous meeting. Today I want to wind up the thermometers by talking about the last two. Those are the pyrometers, which I will split into two, and then also the thermocouple. But just as a reminder, during our previous lesson I had hinted about the mode of operation of the thermocouple, and I mentioned that the thermocouple works on the basis of the Seebeck effect, whereby I explained that the Seebeck effect is the effect of setting up an EMF when two wires of different conductivity are joined together, and then at one junction is maintained at a lower temperature compared to the other. We shall always have an EMF that will be generated across that arrangement. I indeed mentioned that the origin of the EMF is due to the fact that at the hot junction, or what some people call the reference junction, so I say that this is usually a nice water mixture. But then at this end is what we're calling the cold junction, or what I also call the test junction. And then at this other end is the hot junction, which also we call, sometimes we call the reference junction. This is the reference, and then this is the test. So up here is a galvanometer, then these are metal wires. Probably this is made of copper, and then maybe this is made of steel. So I mentioned that when we have such an arrangement, due to the higher temperatures at this end and the high conductivity of the copper compared to the steel, electrons are going to be energized within the copper wire such that they will start drifting across this wire following this direction. Now when the electrons reach this point, they are going to start depositing themselves around here. But due to the fact that electrons are leaving this end is going to seemingly become the positive terminal of our thermocouple. And then since electrons are depositing themselves at this end will seemingly behave like the negative terminal of our thermocouple. So At the end of the day, the electrons which are depositing themselves here and making this behave like as if it's negatively charged, and the ones which left this making this behave like positively charged, a PD is going to develop across this other wire, such that the electrons will continue to be attracted by the positive potential this side, and therefore completing our circuit. And I mentioned that that is what we are calling the Seebeck effect. Now, we know, according to the theories of convectional currents in electricity, whenever electrons are drifting from one end to another, then it means that there is an EMF or a current that is induced within the loop, which will always flow now in the opposite direction to the direction of flow of the electrons. So this is what gives the origin of the mode of operation of the thermocouple. So assuming I want to determine the unknown temperature somewhere, what I'm going to do is I'll start by immersing this into a steam mixture, assuming I want to establish the unknown temperature on the Celsius scale. Then, of course, according to the science, we have said that the EMF will only be generated if at all there is a temperature difference, which is in a manner that this one must be at a lower temperature compared to this other junction. Now, we know that the method of determining the unknown temperature on the Celsius scale requires that we have the fundamental interval, which is the difference between the thermometric property value at the steam point minus the difference between the thermometric property value at the ice point. But now, if I want to establish the EMF generated as a result of putting this into contact with ice-water mixture, then it means that these two, the reference junction and the test junction, will be at the same temperature. And therefore, we shall not have a temperature difference, which means that the Seebeck effect will not kick in such an arrangement. Why? Because there is no temperature difference. In order for this to happen, there must be a temperature difference. Now, for those of you who are going to go on and try to read about the thermocouple in the different reference books, you're going to discover that even for the Celsius scale, the unknown temperature will be determined as E theta divided by E100 times 100 degrees C. Reason being, the thermometric property value when the test junction is in the ice-water mixture will yield 0 EMF, since now the reference junction and the test junction will be at the same temperature. So when this goes to 0, definitely it means that we are leading to this. So usually in the explanations that you're going to come across for the mode of operation of the thermocouple, they will straight away mention that test junction is immersed in steam at the temperature of boiling water, or boiling water at the temperature of steam, and then the reading of the galvanometer or the voltmeter will be recorded as E100. Then after that, this will be immersed in the substance whose temperature is to be determined, and then also again we take the reading, which is E theta. Now, this point is usually a voltmeter or a galvanometer, depending on the gadgets that you're using. Of course, if it is a voltmeter, then it must be a very sensitive one, because I mentioned that these EMFs are usually not of very big magnitudes. They are of the order millivolts. So that's why in most of the diagrams you're going to realize that this will be a galvanometer, because the galvanometer is very sensitive to such small PDs. So if asked to describe how you can establish the unknown temperature of a substance using the thermocouple on the Celsius scale, then these are the steps to follow. Number one, we're saying that place the test junction, or what you can call the hot junction, into want to say in contact with steam at the boiling point of water. Record the reading on the galvanometer E100. Then place the test junction in contact with the substance whose temperature is to be determined record the galvanometer reading E theta. The temperature, the unknown temperature of the substance is then calculated from theta, it's E theta, out of E100 times 100 degrees C. Now, assuming you are required to determine, to establish the unknown temperature on the thermodynamic scale. Now, on the thermodynamic scale, we shall go through the same procedure, only that this time we are going to begin by establishing the EMF generated between the two wires when the hot junction is immersed in a mixture of steam, ice, and then also water vapor, in order to establish the thermometric property value at the triple point of water. Because I mentioned here that the triple point is the temperature at which all those three states coexist in equilibrium. So we are going to first of all establish that, and then after that we shall transfer this end and then place it in contact with the substance whose temperature is to be determined. Now, at the end of the day, the definition for the unknown temperature, T, will be as follows. Note, if required as to establish the unknown temperature on the Kelvin scale, or what we call the thermodynamic scale, number one, we shall establish the EMF, comma, E triple point between the two wires when the test junction is immersed or put in contact with a mixture at the triple point of water. And then after that, we shall establish the EMF, comma, E capital T, corresponding to the unknown temperature. So, this unknown temperature, capital T, at the thermodynamic scale will now be given by the value E triple point times 273.16 Kelvin. Like we have seen with all the other types of the thermometers, they have advantages and then also disadvantages. Now, quickly, what do you think are the advantages of using a thermocouple? For starters, we shall all agree it is not bulky, because you cannot compare the thermocouple to the platinum resistance thermometer or to the constant volume gas thermometer, whereby the apparatus itself, it's a bit bulky. As much as it is not as portable as the liquid in glass thermometer, but we can also say that it is not bulky in comparison to the constant volume gas thermometer and the platinum resistance thermometer. It is not bulky, unlike the platinum resistance. Unlike the platinum resistance thermometer and the constant volume gas thermometer. Number two, it can measure rapidly changing temperatures. Why? Because the thermometric property that we are using is that whenever there is a temperature difference, then there is an EMF that will be generated within the what? Within the two wires. So, due to that fact, the thermocouple, unlike the platinum resistance thermometer or the constant volume gas thermometer, even the liquid in glass thermometer itself, has that advantage over all the others, that for it, you can be able to measure rapidly changing temperatures, because whenever it detects a temperature difference, the magnitude of the EMF generated will keep on changing. And as a matter of fact, I'm going to show you an equation that is relating the magnitude of the EMF generated within this type of thermometer and the temperature difference between the hot junction and the cold junction. And then lastly, it can be used to measure the temperature at a point. Because as we've seen, that the test junction is just two wires that are meeting at a point. So these ones we can easily place somewhere. Unlike the platinum resistance thermometer, where we have to move that silica tube containing the dummy leads and then also the platinum wire, it's a bit heavy. Unlike, of course, the constant volume gas thermometer, where we have to carry along the bulb, the glass bulb containing the gas. So for them, they have that challenge of measuring the temperature at a point. But even the thermocouple can help us determine the temperature at a point. But before I forget, I must also mention that thermocouples can be used to measure quite a wide range of temperatures. They can measure the temperatures between maybe negative 2000 degrees C to 16,000 or 2000 to negative 1200, depending on the nature and the materials of the two wires that have been joined together. So that's also important. Saying depending on the nature of the material of the wires that were joined together. So, among the disadvantages Of course, I know that people will come across other advantages, like it is cheap and easy to construct. But that one I've not given here, though it's also an advantage which is acceptable. But as far as the disadvantages are concerned, I'm going to again leave that as an assignment. I've already talked about the school kit application, which is available at the moment on the Google Play Store for Android users, and then the iOS users. At the moment, we do not have a version of the application, but very soon we shall also be launching it. Kindly go there and then you join my forum where I'm sharing a lot of this learning material that I'm using here. Like I say that nowadays it's very difficult people accessing me on the email because my email is already full. So whenever people try to send an email, I don't receive it. But I'm going to leave, I've already left an assignment on a thermometry under my forum on the school kit application. And at the end of today, I'll also be leaving another assignment and indeed also providing all these notes that I'm using. The disadvantages I'm going to talk about only one, which is to do with the variation of the EMF generated with the thermocouple, with the temperature difference between the hot and the cold junction. I want to bring to your attention the fact that when they are calibrating this type of thermometer, because it is present in the calibrated form, and in the calibrated form, the voltmeter or the galvanometer, which was included up on my diagram, has already been calibrated in order to give us direct readings of the temperature. But during the calibration process, what they discover is that the EMF generated is related to the unknown temperature theta by such an equation. And as you can see, this equation is a quadratic equation in theta, indicating that it either has a maximum point or a minimum point. But mathematics will confirm to us that such an equation has a maximum point. I know that the physics students who are also doing mathematics have probably looked at that topic of quadratics under chapter 9 of Backhouse 1, Introduction to Algebra 1, where we can just look at the equation and then be able to predict, depending on the coefficient of the term that is to the power 2, whether it will have a maximum or a minimum. Now, using the knowledge of mathematics, it is true that that equation is first of all telling us that the behavior of the EMF against temperature, if plotted on a graph, will be something like this. And if this is so, then it means that this curve has what we are calling a maximum point. But the temperature corresponding to the maximum reading of the EMF assuming this is my theta in degrees C, and then this is my EMF E in volts or millivolts. Now, for certain values of the temperature difference, we are going to see that the thermocouple will give us the same reading. You can imagine at a temperature, say, theta 1, and then also at a temperature, say, theta 2. Because this is the relationship between the unknown temperature and the EMF generated. So it is communicated to us that there are two temperatures for which you're most likely to get the same reading of the EMF. And therefore, the thermocouple is not good for measuring temperatures which are above its neutral point. This one I'm going to call the neutral point. That if you go beyond these temperatures, then you're most likely to start getting repeated values of the EMF. And this is one of the biggest disadvantages of the thermocouple. However, I am not going to go into the details of how we arrive at this, but people who are curious, you can use Tom Duncan and also the internet to go through the procedures of how they arrive at this. Otherwise, at this level, we must know that that is the behavior of the values of the EMF if checked against the temperature differences between the test junction and the cold junction. So the disadvantage that it is not good for measuring temperatures above its neutral point is because of that fact, that once you go beyond a certain value of the temperature, then you're most likely to start getting repeated values of the EMF that you have already got before, which means that now you will not have clear information. Why? The thermocouple is going to behave like as if it is reading the same temperature, yet they're supposed to be different temperatures. So, with that being said, I want you to go and participate in the research and then also find out other disadvantages of this type of thermometer. Otherwise, this wraps up the common types of thermometers, or the ones which are used to measure temperatures at points and bodies which are not so hot. Because in the section of the pyrometers, I want to mention that the pyrometers are a special form of thermometers which are used to measure very high temperatures. I'm talking of temperatures which are greater than maybe 3K degrees Celsius or even in Kelvin. So in such cases where if you were to insert maybe a liquid in glass thermometer, it will quickly be vaporized due to the high temperatures there. I mean, you cannot even stand next to such bodies. I wish to determine the temperature of the sun. I wish to determine the temperature of a furnace. Let me use a practical example. For example, I wish to determine the temperature inside the furnace. It's so unlikely that you throw in a glass bulb or insert the silica tube containing the platinum wire or even the liquid in glass thermometer itself, and you get a reading, because temperatures there are really hot. They are so high. So in such cases, what we do, we employ the pyrometers. The pyrometers come in two versions. There's what we call the optical pyrometer, and then there's also what we call the total radiation pyrometer. What is the difference between the optical and the total radiation? The optical form of the pyrometer responds or is sensitive to radiations which are in the visible light region, while the total radiation pyrometers, for them, they are sensitive to radiations which are both in the visible light region and then also in the infrared region. Of course, for such a hot body, in order for us to determine its temperature, we shall base on the nature of the radiation that it is emitting. Because later on, I know that if there are some Form 6s who are watching me, then they have heard of this under the topic of radiation. But nevertheless, given time, I think I'll also be tackling heat transfer for the Form 5s as far as this section is concerned. We know that the radiation emitted by a body is determined by, number one, its temperature, and then this will give us information on the wavelength of such a radiation. So if I can be in position to detect the presence of a certain radiation and maybe also come up with a value of its wavelength or the frequency, then it can give me information on at what temperature is the other body. And this is usually associated with the colors that the bodies will be emitting. We've all seen a flame which is blue in color, but then we've also seen a flame which is red in color. We've also seen a flame which is yellow in color, and then we've also seen what we call the white hot bodies, whereby it's glowing white, almost white. Of course, this may not be so much common, but when it is glowing almost white, I don't know how many people have made this observation with the charcoal stove. There are those times when it's really lighting. You will see a series of blue flashes, but somewhere you also see that whitish nature of the flame, and that's where it's hottest, according to the theories of radiation. But I want to spare you that physics for now, and then just try and hint about the pyrometers. because I know that the pyrometers are supposed to be in the two sections. We talk about them in thermometry, but then also under radiation as detectors of radiations. So, let me give you something to write down. I hope that my viewers out there are following me, and probably, I know I'm not doing a lot of writing, but I expect you to be doing a lot of listening and then using the necessary resources plus the learning materials that we have available. We shall be in position to make some good notes by ourselves. But still, I'm going to leave notes about this under my forum. So, I'm talking of pyrometers. And I've mentioned that there are two types, one being the optical pyrometer, and then the second one being the total radiation. So I mentioned that, let me try and give you a brief insight of how the optical behaves. I think next time I'll try and provide a video on this. Then I'll also try to give you an image. So on the other side, I have a filter. Sometimes the radiations could be of very short wavelength and therefore possessing a lot of energy which can cause damages to our eyes. The fact that I'm including a telescope means that this is the extension of this type of thermometer is an optical instrument, which is a telescope of a kind. So I'll have radiations coming out of my hot body and then being brought to focus at such a point. I'm going to beg my producer to bring up this diagram, because I'm sure we have it somewhere. So this is what we have. Looks something like that. This is a variable resistor, R. This is its sliding contact. Keep varying in order to adjust the current flowing through the filament. So here is where I have my filament. This is my red filter. This is my eyepiece. Of course, this is the objective now. Optical instruments in form of telescopes have got what we call the objective lens and then also the eyepiece lens. This could be my hot body, e.g. a furnace. So there we have. This whole thing is a telescope consisting of those two lenses, the objective lens and then also the eyepiece lens. Now, what exactly happens during the use of this type of thermometer or detector of radiation? It is a thermometer, and at the same time it's also a detector of radiation. So what we do, we're going to focus the telescope. I'm going to beg my producer to look for an image of the optical pyrometer. Yeah, it's present on the internet. There is an image which is in form of a gun. And by the way, I must also bring it to your attention that what we are calling the infrared thermometers, or the common types of thermometers that now people are using, which are in the form of a gun. Some people call them the gun thermometer, but they're actually called infrared thermometers. I'm going to explain them because their mode of operation, its background is the pyrometers. They are a modern form of the pyrometer, of the total radiation pyrometer, because it is the total radiation pyrometer which I told you that for it is sensitive to the visible light form of radiations, but then also the infrared form of radiations. And our bodies, due to the heat or the temperatures at which they are emitting a certain form of radiation, which is in the group of the infrared radiations. So I'm going to be talking about how they're exactly working. But basically, it's like this. Now, in the optical radiation pyrometer, what we have is the telescope with its objective facing the source of the radiation, e.g. a furnace. This is done at quite a distance because I've told you that here we are dealing with very hot bodies. So you can imagine that the distance between this and this is maybe even 5 meters, which is around 500 centimeters. So you're standing at a certain distance from the source of radiation because you cannot be very close to it since it's very hot. So what happens is that we try and focus light coming from the furnace or from the hot body, so that will bring its image at this point. Now, while looking through the eyepiece, we make observations on the colors or the nature of the color of the filter. Experiments show that, remember this filament, the colors of the filament. This filament is connected to an external circuit, this side. The external circuit, the purpose of the external circuit is to heat the filament and then bring it to the temperature that has been focused here, that is coming from the hot body. If the two temperatures here are the same, then the ammeter, usually which is calibrated in degrees Celsius or Kelvin, will then give us the reading of the approximate temperature of our hot body. I want to be very clear on this, and allow me explain myself again, that we are going to focus radiations from a hot body at this point. But again, at this point will be the image of the point that we are focused from this side. We have seen this during the light experiments, the optics experiments, when we're in the lab, whereby we try to focus the source of light, which is the filament in the bulbs that we're using during the practicals. And then we get maybe such a point, and then we shall call that sharp and clear, or sometimes we can form either that or that, where we shall say that that is maybe sharp magnified during the practicals, the physics practicals in the lab. I know that my students out there understand what I'm talking about, because these are observations that we make when we're in the lab. So it's the same thing that is happening here. I'll pick my particular point from the source, and then I'll focus it at this point. Even the red diagram shows it. But at this very point, I'll also be in position to view the filament which is connected to one external circuit. Now, if this temperature here is higher than the temperature of the filament, what is going to happen is that the filament is going to appear dark on a bright background. We're going to have such a spot because of lack of time, but I know that next week this is what I will start with. I'll try and show you this exact spot using an animation, because there's an animation which is present. Or people should go and look it up on YouTube. There's an animation which is trying to explain the effects of the temperature of the filament as far as trying to determine the temperature of our hot body is concerned. Because we always make that statement that if the hot body is at a higher temperature than the filament, then the filament is going to appear dark on a bright background. Indeed, this one will be of a dull color, maybe black, brownish like that, but then this will be a bright color, depending on the radiation coming from it. Maybe if it is emitting red light or yellow light or blue light, then that is what we shall have here as the background. So adjustments are going to be made in the external circuit so that the color of the filament matches the color of the background. Now when that, in trying to adjust the color of the filament, we are increasing its temperature. Why? Because we are making adjustments on the rheostat, which means that we are controlling the magnitude of the current flowing in this circuit, which is contributing to the heating of the filament. If you overheat the filament beyond the temperature of our hot body, then the filament this time will appear bright on a dark background. The filament will seemingly be brighter compared to the background. However, during the mode of operation of this instrument, we adjust the rheostat so that the filament is at the same temperature as the temperature of the source. And how shall we know that we have achieved that? The filament is going to be of the same color as the background such that you cannot distinguish them. Now that will mean that both of these are representing the same type of temperature. Now, in the standard application or operation of this pyrometer, this ammeter is already calibrated to give us a reading of the temperature of the filament, of which once adjusted so that it is of the same color as the background, which means that it is at the same temperature as the hot body. We shall now consider the reading of the ammeter to be our unknown temperature of the furnace or the hot body from this side. Kindly let people go on YouTube and search mode of operation of the optical radiation pyrometer or the optical pyrometer. You're going to find an animation which is having this arrangement, and then they are trying to explain it. I hope that people manage to find it. Otherwise, I'm going to leave a link on our app whereby people can use and then they go and visit this. Because of time, I would like to thank you for being good viewers and always tuning in to this show, Somera Muddiirolyo. We want to assure the general public out there that for as long as the pandemic is still alive and kicking, the management of the central government and of course the station itself are still committed in ensuring that this educational show goes on. So kindly always tune in, even if there are changes in times, kindly make sure that you're always tuned in order to benefit. Otherwise, I would like to wish you the very best of the remaining part of the day, and may the good Lord bless you all.
Somera Muddiirolyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi lusomesa arts ne sciences okuviira ddala ku siniya esooka.